Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started with the webinar today, I have just a couple of administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the participants joining us today. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll follow up with you after the webinar. Today's webinar will focus on PlumeStop liquid activated carbon with a technology overview on in situ containment of PFAS. To give us insight into this topic, we are pleased to have with us today Regenesis Manager of Research and Development, Dr. Kristen Thorson. Dr. Thorson is the lead inventor of PlumeStop liquid activated carbon. She heads the Chemical Research and Product Development Program at Regenesis. Her team is focused on developing advanced technologies for the treatment of recalcitrant compounds in mixed environmental media. We also have with us today Regenesis Southeast District Technical Manager, Chad Northington. Mr. Northington has over 15 years of experience as an environmental engineer and project manager. His engineering experience includes remediation system design and installation, site investigation, and technical assistance across a broad spectrum of project and contaminant types under various regulatory frameworks. All right, that concludes our introduction, so I will now hand things over to Chad to get us started.
Thanks, Dane. Am I coming through loud and clear there?
Yeah, you sound great.
Excellent, thank you. Well, let me begin by thanking everyone for their time and interest today in discussing this important topic of containment of perfluorinated compounds. You'll also hear us use the acronym PFAS, short for per and polyfluorinated alkyl substances. So as you know, PFAS is quickly moving out of this emerging contaminant category to more of a quote-unquote standard contaminant that will need to be addressed as kind of a new player under this remedial and drinking water regulatory frameworks. My observation, as I've been watching this evolve a bit, has been that for those sites where efforts have been made to address these impacts, the industry is starting to return to the stone age of remediation, where pump and treat systems are being used to address this new challenge. For a class of compounds, as you know, are resistant to the standard suite of technologies that we have available as remedial practitioners. So today we're going to discuss a technology that's going to get us away from that, away from the challenges and some of the pitfalls of pump and treat that I'm sure many of you are probably already familiar with. We put together a presentation I hope that you're going to find to be both informative as well as innovative. That's something that Regenesis has been a quality of who we are for over the last 20 years, as we're constantly seeking to find these new solutions to these new challenges that are happening below the subsurface. We've been in the process of developing and now implementing PlumeStop for quite some time. It's demonstrated its effectiveness in quickly remediating petroleum hydrocarbon and chlorinated solvent sites across the globe now, and now we're exploring its ability to also provide a fast-acting solution to groundwater impacts for these class of compounds. This has been a top priority for both the research and development team, as Kristen will explain today, as well as for the remediation technology division that I'm a part of, as we're starting to actively seek sites to implement this technology at the field level. Our success has been speaking for itself. It's been a testimony, I think, to what PlumeStop has done with other contaminant classes and what its potential is for this particular contaminant class, as you're going to hear today. So with that, I will pass things over to Kristen for this discussion on PlumeStop liquid activated carbon and its applications.
Great. Well, thanks, Chad, and thanks, Dane, and thank all of you for attending today and those who are responsible for getting this set up. It's really always great to have these kind of opportunities to discuss our relatively new technology called PlumeStop liquid activated carbon, and really to just highlight the features of this particular form of activated carbon that opens up some new applications to employ the benefits of activated carbon that were really previously not possible. And so today that focus is going to be on the in situ containment of fluorinated compounds. So I'm not going to spend too much time going through the background, as I'm making an assumption that most people are at least familiar with this problem. However, I do want to highlight the problem in light of what the difficulties and challenges are in addressing them in groundwater and soil. So when we talk about per and polyfluorinated alkyl substances, or PFAS, we're really talking about a very complex mixture of fluorinated compounds. As I think most people are aware, PFAS and PFOA are the two that get the most attention these days. However, that is expanding, and those correspond to the species that have a 8 carbon chain length. However, there is a really wide variety of chain lengths and different functional groups that are present in these plumes. And so that's just an important thing to keep track of as we develop technologies and also as we implement them, that to know that we're not just dealing with these 2 compounds in particular, although we have also focused on those so far. We're aware that the environmental problems associated with these compounds is really due to the fact that they've been used widely in various products. And I think it's important to point out that the difficulty in treating these particular compounds has to do with the properties that made them useful in these types of products. So they're used in firefighting foams because they don't burn, they don't thermally degrade. And they also have oil and water resistant properties that really make them useful in the various food containers and other applications in which they've been used. Overall, the key part or the key property is that they're really stable. And so that is the difficulty that we have to address, is that in the environment they're also stable. And as Chad pointed out, they're just hard to break down, and so they are going to be very persistent. And the reason why we're all talking about these and concerned is because of the probable links to human health issues. So what does it look like when we're trying to address this type of a plume, a fluorinated compound plume in the soil and groundwater? I attended a talk about a year and a half ago at Battelle in Miami. This was by David Woodward at AECOM, and he pointed out some various characterizations of these plumes after looking at, I think he said, several dozen of them. And some of the key points that stood out to me were the fact that these are relatively large plumes. He said most of them are greater than 1 mile in length. This map over here on the right shows a plume that's actually about 4 miles, and you can see there's question marks on that map because he noted that many times they can't even find the front of the plume. So in fact, they might even be larger than this. So it's just a really vast, ginormous problem. And then layer on top of that the fact that more than 3/4 of those plumes tend to be at very low concentrations, usually in the low parts per billion and even into the part per trillion type concentrations. So large dilute plumes, it doesn't really matter what the contaminant is, that just makes them difficult to clean up. And obviously, because of the health concerns, there has been this new health advisory limit set at 70 parts per trillion. So that only kind of adds to the difficulty. We're starting at low concentrations and needing to get to even lower concentrations. And again, that just is kind of a recipe for, doesn't really matter what the technology or again what the contaminant is, those levels are hard to treat and those levels are hard to reach. So these are all things we're having to think about when developing and using technologies. And as I already mentioned, they are extremely recalcitrant compounds, meaning that so far to date, the tools we have in our toolbox with the conventional treatment methods that are useful for our chlorinated solvents or petroleum hydrocarbons just have not been effective to date. And that includes the fact that at this time there are no known bacteria capable of completely biodegrading these. As a chemist, I'll point out that that's kind of where I put a lot of hope in the future. I always kind of hope that the bacteria can rise to the occasion and that will help us out down the road. This table, I apologize if it's a little bit small, but we can kind of get the gist of it by looking at the colors. This was just put out recently this year. Chris Higgins out of the Colorado School of Mines has done a lot of work in this area, and he really kind of summarizes some of the technologies that are out there and is demonstrating that many of them are just not feasible or to remove these types of compounds. So the fact that they are not volatile means that air stripping or aeration just doesn't work. Conventional oxidation has not been useful to date. You do see over here on the right side a couple of promising ones, nanofiltration and reverse osmosis. However, there's usually a price tag associated with those. And so then we see this column here for activated carbon, and that's, so far where we found one of the most effective technologies to date. It's useful across a wide range of these compounds. It's important to note that not every compound has the same efficiency with activated carbon. So, we hear about some of the shorter chain compounds not absorbing as well, and they're going to break through a little bit more quickly. So that, as Chad already mentioned, the currently accepted method, what we have right now in our toolbox to remediate and treat contaminated groundwater with these fluorinated compounds is to use pump and treat and pump it through a granular activated carbon bed. And again, that has been quite successful. Of course, there's a rather expensive operating and maintenance fee associated with that, and then also the need to take away your spent carbon and just dispose of that. That also has a fee associated with it. But again, it's where we're at, and it's what is working the best right now. So that brings up the question of, knowing that activated carbon is working for us, are there other ways we can employ it? Can we use it in situ? And that's really where we're going here today. And before we get into it a little bit further, I would just like to take a moment to kind of plant the seed of the idea of using activated carbon ex situ versus in situ. I think there's a couple of key differences there. So when we think about pump and treat, you have very short residence times. The time that the contaminants are in contact with the activated carbon can be quite short. Obviously that can be designed for, but it's just something that needs to be very efficient in that case. And then also under pumping conditions, when you're talking about tens to hundreds of gallons per minute, that means that the flux rate going through those carbon beds is quite high. And that directly is going to impact how long those carbon beds are going to last. Now if we think about using activated carbon in situ, what we're really trying to do is move away from those pumping conditions. And what that is going to give us is longer residence time, so more contact between the contaminants and the carbon. Because we're working under passive flow conditions, we can use the natural flow of groundwater, which also means that the flux rates are going to be much lower too, which again is going to correlate to how long this carbon is expected to last. And that's what we're going to go through about midway through this presentation. So let me take a moment now to introduce this technology. So this is the fun part of my job. This is what we work hard to do in the lab here, and kind of bang our head against the wall sometimes, but we have rewards on the other side. So this has actually been a project that's been going on for even 10 years. We had this idea to create a technology where we could implement a sorbent into the aquifer, and we've gone through various iterations, but about 3 or 4 years ago we set into the idea of using activated carbon. And also, as we went through these different iterations, there were a couple of critical functions that we really wanted this technology to have. The first is its ability to distribute in the subsurface. And that's really key to make sure that we get that contact between the technology and the contaminants. We also didn't want to have to frack it in. We wanted to be able to inject this under low pressure in order to have a little bit more control of where it's going. As it's based on a sorbent, it needed to be able to absorb contaminants quickly. This is really useful to prevent further migration and also just to reduce the risk of having those contaminants still be present in the groundwater. And then a final bullet point there is that while trapping the contaminants is great, we also, in the event that there is a biodegradation pathway, we wanted to be able to couple those two together and really have it promote biodegradation. Of course, as I already mentioned, we don't have a biodegradation pathway with the PFAS compounds, so I'm not going to get into that aspect of the technology at all, but it has been important for us with other contaminants like the solvents and the petroleum hydrocarbons. So what came out of this development is Plume Stop liquid activated carbon, which you can see a picture of there. And the simplest form is that it's a non-toxic black liquid. Again, it's based on colloidal activated carbon, meaning that it's approximately 1 to 2 microns in size. And that's really important for our ability to distribute it in the subsurface. If we get too large, as you can imagine, it's just going to get filtered out very quickly. This allows us to have it migrate through various pore throat sizes. And along with the sorbent, it's comprised of food-grade polymers and additives, which is what stabilizes it and again allows it to move through the subsurface. So what does it work on? Well, we really already know the answer to this because again, it's based on activated carbon. So anything that you already know activated carbon to be useful with is where we can use plume stop. So as we've mentioned, chlorinated solvents and petroleum hydrocarbons is where it's really been used the most over the last couple of years since its launch. We have quite a bit of data on that. But again, pesticides, a lot of different organic chemicals that have that affinity for activated carbon are going to work. And so we include on this list PFAS because we already know it's being used in these ex situ systems. So the outline for the rest of the talk is really going to be looking at these key processes between plume stop and PFAS and how we can manage these plumes. So that will include the ability to distribute plume stop in the subsurface. That's the first hurdle we have to get over. If we can't get it in the ground, then we're not going to be able to use it. Then once it's in the ground, we'll talk about the actual absorption with PFAS and what we can expect. How long do we expect it to last and how can we predict that? And then we'll end with a few in situ containment strategies. So when we're looking at these large plumes, where might plume stop be useful? So we'll start with the distribution of the subsurface. As we were developing plume stop, we ran probably close to 1,000 of these columns to really optimize the formulation. But this demonstration, I think, really shows you what plume stop is capable of. So these are, relatively small columns. They're 1 inch diameter. They're about 1 foot long, and they're filled with a sandy soil. It does have about 10% silt and clay, so it's not a clean sand. And they're completely operated by gravity feed. No pumping here whatsoever. And so for this demonstration, I'll show you liquid activated carbon on the left as compared to a commodity powdered activated carbon on the right. In both cases, they're the same concentration of activated carbon. And the time lapse I'll show you next is you'll see the activated carbon being loaded onto the column and then subsequently flushed with about 3 pore volumes of clear water. So if you look at this, I'll first draw your attention to the powdered activated carbon. You can see it just really doesn't go anywhere. It's filtered out in about the first half or 1 inch of the column, as it doesn't have any of those distributable properties. Now if I show you one more time, as you can see in the liquid activated carbon, it readily distributes evenly throughout the column, again all under gravity flow. And perhaps one of the most important parts here is the staining that happens. So as I mentioned, we ended this column study by flushing with 3 pore volumes of water. And you can, I think, hopefully easily see that there is a staining of the soil as compared to the color that it was prior to its application. So that is really key because we want it to distribute through the soil. However, if it would continue to move forever, we would just have a plume of liquid activated carbon, which really wouldn't help us out at all. So the key part is that it can distribute and then lock into place by adhering onto the soil, which we call deposition. And we've also made an analogy to painting the subsurface with activated carbon. I really kind of like that idea because it kind of gives the idea of it moving through the subsurface, leaving a coating as it goes. And when we talk about that, I tend to be a little bit more visual, and I think that idea of deposition is a little bit abstract. So to give you perhaps a visual, here's a scanning electron microscopy image. On the left is a clean sand, and then on the right is that same sand where plume stop has been deposited. On the bottom here, you can see the scale of 50 microns. So these little dots here basically represent the colloidal activated carbon particles throughout the different surfaces. So that's really what we mean by depositing and or painting the subsurface with activated carbon. And I'll point out that in that column study, we flushed with 3 pore volumes of water. However, it could have been 3, it could have been 30. Once the plume stop has deposited, we do not see washout, so it really has permanently fixed itself there. So there are quite a few questions that we get regarding the distribution, and a couple of those here would be, well, what about the distribution in low perm zones? And how can you address contamination in clays? And what about the radius of influence? And I think to answer these questions, we need to look at where do we really want to be putting the plume stop, or where do we need to be putting it. So if we look at this cartoon of an aquifer, and like I would guess nearly the majority of most aquifers, is that there is a heterogeneity to them. So they're going to have, you know, gravel and sand zones, and they're going to have silty clay zones. And what that creates are higher permeability zones, or highly conductive zones, and lower permeability zones. And in the end, the higher permeability zones end up being our plumbing of the aquifer, our, you know, our pipelines. And that is where the majority of the water is actually going to be transporting through. And as a result, if we use orange to represent contamination, those same higher permeability zones are also going to represent how the contaminants move. This is what is responsible for those plumes getting very, very large. Those are the avenues that the contaminants move through as the principal flux zones. And then as they're moving through those zones, they will forward diffuse into the lower permeability zones, like those clays, and that acts as residual storage. So I think the main point here is to think that when you see contamination in clays, it's usually not because they have directly transported through those zones. It's because they've come through the higher perm zones and then diffused into them. And so that's important to consider when we want to, or where we want to be putting remediation agents. So in the next frame here, we can see that those high flux zones are the zones we try to target with plume stop. And plume stop can be applied either, you know, direct push, injection wells, but we do a lot of work prior to the application. We call it design verification, to try and identify those high flux zones, because one, that's where we know we can successfully place the plume stop. Just like if we tried to inject water into a clay zone, we're really not going to be that successful. So the zones where we can get distribution of plume stop, it's going to be those higher flux zones. And as we saw in the column study, when we inject the plume stop into those zones, we're going to paint the material in there and to make a permanent coating of activated carbon across those zones, which then also allows us to deal with and treat the contamination that is in those low perm zones, because at some point we will see the back diffusion of contaminants coming out of those storage zones back into the high perm zones. And we've really set ourselves up with like a catcher's mitt by permanently emplacing the activated carbon, so that when they do back diffuse, the plume stop is sitting there ready to absorb it. And in that way, we have addressed both the low and the high perm zones of contamination. And when we think about the radius of influence, because we know we can inject into the high perm zones and it's leaving an aquifer, the radius of influence that we'd expect really is going to be directly related to the volumes we put in. And so again, we can look at the particular aquifer material to get an idea of how far we expect it to go. And I'll show you in a moment that we have seen in highly permeable zones that we have really great distribution of plume stop, and we expect to be able to put or inject in plume stop on wide centers, because it will flow readily in those zones. And we can actually see this really nicely. This is a soil boring taking post plume stop application, and hopefully you can see here that at the bottom of the soil boring, it's very impermeable clay here. So that represents here where water is not going to be flowing, and also where we're not going to be in placing plume stop. However, up here in this zone, you can tell it's a little bit more sandy, probably a little bit even gravelly and silty, and that's exactly where we put the plume stop. And that's also where the water is going to be flowing, so we have successfully placed it where we need and want it to go. So that was a field example. I'll also point you to an ongoing study we have right now in the laboratories. We are working with Tom Sale at Colorado State University and also Kevin Saller from CDM Smith to do a kind of a fun study where we look at back diffusion. We have a couple different objectives here, but one of them that's come out of it has really been this idea of transport. And so these tanks, which Tom Sale is kind of known to be a pro at, are set up, and you can see these altering layers of different types of sand and silt. And so what we've created are these high and low permeable zones. These tanks are operated in upflow, So we have water and anything else we inject into them going from the bottom to the top. And again, we have a couple different objectives looking at back diffusion and biodegradation, which hopefully we'll have data on in the future, not relating to PFAS, but other contaminants. But for the purpose of this talk, I just want to show you the transport portion of it. So when we applied the plume stop, we injected it at about a volume of about 1 pore volume. And then it's been followed since then with clear water flushing. And some pictures of the results of this show that it's very easy to identify where the sand zones were. You can see that plume stop has completely coated all the sand zones, the higher permeability zones here. And I think what we were pleasantly surprised with is that the penetration we're seeing into those low perm zones. So again, the formulation of plume stop allows it to even work its way into some silty zones as well, which is just going to help us down the road when it comes to remediation. It's going to be a little bit more effective because we've impacted a wider area. I'll point out that this picture was taken after plume stop had been applied and after even about 20 pore volumes of water had been run through it. So again, you can see that we haven't flushed out the plume stop. This is a permanent staining. We don't have the plume stop continuing to move with the groundwater. It's permanently painted on there. And if I just turn it to the side and bring it back to the cartoon, I think we can really see this an idea of we're able to put the plume stop in the same zones where the water is flowing so that we can really capture that flux, or the contaminant flux. So the last sort of application point I'd like to make, and I'll just touch on this briefly, I'm not going to go through too many details, but again, we had done all these small columns in the lab and we wanted to try and scale that up to something a little bit more field relevant. And so we constructed this 16-foot column in our warehouse and filled it with the sand and basically just wanted to confirm that plume stop would be able to go that full 16 feet, that it wouldn't self-clog, we wouldn't have any other issues as we're injecting it across a longer range. And so in this case, we have this little pump. We filled this up with plume stop and then pumped it up through the column and then collected everything coming out. And all this throughout, we monitored the pressure, and at no point did the pressures ever jump up, so it was all low pressure installation. And the key conclusion here is that we were successful in being able to transport plume stop across these 16 feet. And we actually believe that if we could have a longer column, if we had a taller warehouse, we'd be able to have even probably double that. There was no issue injecting it through 16 feet, and it probably would have continued to go on. Here you can see as it's approaching the 4-foot mark, you have this nice plug flow. We're not seeing preferential pathways. And then same thing as it's approaching the 16-foot mark, and it did go all the way through, and we continued to pump through, and again, did not see any kind of clogging occurring whatsoever. So, all these point to the idea that yes, we can get plume stop into the ground, and we can successfully distribute it, which is going to be key for, the next question is, okay, we can get it into the ground. Now what can we expect from it? How is it going to absorb, and what's that going to look like in particular with reference to PFAS? So for any contaminant that we want to treat with plume stop, we need to understand the dose response. So we need, in order to be able to design and know how much plume stop needs to be put in for a given amount of contaminant. And to do this, we measure the isotherms of the contaminant with plume stop. And we can do this here in our R&D lab that we have at our corporate headquarters. And so we did that for PFOA and PFAS, and we're continuing to look at the broader range of compounds that make up the PFAS suite. And really what an isotherm is the partitioning equilibrium. So we're able to understand for a given amount of contaminant how much goes on to our sorbent and how much remains in solution. And then we fit it to a Freundlich equation, and this fit is what we can use to do our calculations of how much plume stop is required. Now, unless you work with isotherms on a regular basis or are just very familiar with them, these values are pretty meaningless. It's hard to understand whether these are good or bad values. And so it brings up the question of, well, how else can we be interpreting these isotherms? And so we have been working for the last couple of years, and we continue actually to work on this with the idea of being able to integrate these plume stop doses into existing fate and transport models. So the idea here is to be able to use those isotherms that we measure in the lab and incorporate them into these existing models, which would allow us to predict the longevity of plume stop dose and then further even optimize the dose to meet a desired longevity. So if you need a certain amount of time frame to be captured, we can see how much plume stop would be required. So we have been working with Professor Arturo Keller at the University of California at Santa Barbara to do just that. We have started using the BioColor model, which perhaps some of you are familiar with, and we basically have amended it to include the isotherms that we measure in the lab and also a plume stop dose in order to be able to model what we expect the impact of plume stop to be. So I think the easiest way to understand this is to run through a scenario. So in this case, we'll simulate a PFOA plume. In this case, it will be a plume that's at a concentration of 50 parts per billion. And for the sake of the nomenclature in this model, we'll call that the source. So that's, basically the toe of the plume would be right here at the source. I've made that plume moving at about a seepage velocity of 1/3 of a foot per year. And we'll look at the model through a time frame of about 8 years. So the first thing we'll look at actually is just how much has this plume expanded over the course of 8 years. And then we'll also look at what happens when we install a 25-foot plume stop barrier in front of this plume. And so the barrier will be installed right here. The zone 1 is what allows us to do that. And is what we'll monitor is just down gradient of the plume of the barrier in order to look at how the plume is moving, keeping a target of a down gradient concentration to be less than the health advisory limit of 70 parts per billion. And again, in this model, we're assuming absorption only, no biodegradation. A nice feature of this model is that you can include a degradation component if you have a compound that does degrade, which is something we look at for our solvents and other types of compounds. But of course, here we have turned that off. So now I'll show you the outputs of this modeling study. First, we'll look at the no treatment scenario. So again, just having that plume move naturally at, again, that 120 feet per year is what we see here is that the plume has extended over 1,000 feet at concentrations above 70 parts per billion within 8 years. So I don't even have it, this only shows it going out to 400 feet, but this graph could go all the way out to about 1,000 feet. So a huge magnification of the plume over the course of 8 years. Now we can look at the output of what happens when we put plume stop, and you can see this really striking difference. So now we've been able to actually capture and contain that plume throughout those 8 years. We've captured the PFOA and there's nothing that would elute above the 70 parts per trillion level for those 8 years. The question would be, okay, well, what happens after 8 years? Well, at that point, we will have filled up the barrier and it will start to break through. That's just the nature of, just like in an ex situ system, that's about how much time we would have here. When we think about breakthrough, it's really important. Obviously, this is a single scenario. There are many different things that will go into how long we can expect these barriers to last, including the seepage velocity. So I've done a quick graph over here to kind of describe this, and I think it's pretty logical in that here's seepage velocity on the y-axis, so getting faster as you move up, versus that barrier breakthrough time. How long can we contain the plume? And so the faster that a plume is moving, the shorter amount of capture time we have versus, we can get many more years if it's moving a little bit slower. And this all kind of goes back to that idea of the in situ versus ex situ use of activated carbon. So when you're pumping contaminants through an activated carbon bed, you have a artificially high seepage velocity, and so your breakthrough time is going to be shorter because you're pushing more flux through. Again, versus using these natural flow conditions, we can start to imagine, quite a few years of treatment. Obviously, the contaminant concentration will have a similar type effect. Higher concentrations will break through faster, and lower will be able to be contained for a longer amount of time. The contaminants present, it's important to note that if you have a mixed plume, all of those components are going to go into how long the breakthrough time is of those individual components. So that's something that needs to be considered and be designed for. And then also the plume stop dose. So it's a good thing that we have that in our pocket. If we want to see longer containment, we can put in a higher dose as well. And now all of this really, I think all these different components can be summed up in a different way in a factor that I think everyone may be familiar with, and that is the retardation factor. That's really what we're talking about, is that plume stop has an ability to further retard the plume from what its natural flow would be. So if we take a moment to just think about what this really means. So the retardation factor determines how fast the contaminant moves relative to groundwater. So for reference, if we have a certain groundwater velocity, if you have a retardation factor of 1, it means it's not changed at all. It's going to move at the exact same rate as the groundwater. Versus a retardation factor of 2 means we're going at about 50% of the rate of the velocity of the groundwater. And a retardation factor of 10 means that the contaminant's moving at 1/10 of the rate of the groundwater velocity. And so for, most contaminants, there is a natural retardation factor that exhibits from the natural amount of fraction of organic carbon that's present in the aquifer. And typically, you'll see something in the range of 1 to 5, although again, that's very dependent on what the VOCs are and exactly how much organic carbon is present. And there's a couple of literature values out for PFOA and PFAS that retardation factor will be on the order, of 3 to 20 or so. So there is some natural retardation. However, I think what we're all also used to is that whatever the retardation factor is just what we have to live with. There is no way to change this. But this is really what plume stop is bringing to the table, is that because we can inject it and because we can paint the subsurface, we're now able to actually alter that retardation factor for the first time. So if we look at, again, that same dose that I used in the BioChlor model, we can see what kind of a retardation factor those correlate to for PFOA. So again, it's dependent on the initial concentration of PFOA in this case, and also on its based on its KOC and the isotherms there. But is what we can see is that with plume stop, you can start to have a very, very large retardation factor, something that just is not feasible with a natural fraction of organic matter. We don't see these types of values under any kind of natural conditions. And the story is actually slightly improved for PFAS because it has a more favorable isotherm. And so you start to see even larger values here. And given the fact that these plumes are usually at very low concentrations, the good news is that we typically be on the lower end, so the higher retardation factor when you're using plume stop. And so again, just to kind of emphasize this, is that when we previously could not change the retardation factor of an aquifer, by having the ability to inject and install plume stop, it now really gives us the ability to change that, and that's what we're doing, and that's really what these models are looking at, is the retardation factor that has changed because of plume stop. So if we think about that, in this zone here, it previously had a natural retardation factor probably in that 3 to 20 range or so, if we're talking about PFOA or PFAS. But with the installation of plume stop, we may have increased that by orders of magnitude. And that is all going to directly impact how long we expect it to last. So, with that idea, we can put it in the ground and we know that we can have some good containment over, a period of time under these types of conditions. The last thing I just want to go through is where could this be useful on these large plumes? So we'll go through a couple different scenarios with some cartoons demonstrating them. And the first one is actually very similar to the demonstration I gave with the BioChlor model. So this is a single cutoff barrier that will really limit the plume expansion. That's what we saw in that example. This can be really useful to protect property boundaries. So if you don't want the plume to be leaving your site or entering another site. Also, if there's a sensitive receptor, so like perhaps a body of water as shown here, we have a river that we're protecting, or perhaps a well. plume stop could be installed here to keep that from expanding even further. And then if we look at kind of a time lapse here, assuming we could address the source, and also with PFAS compounds, sometimes the source isn't as persistent as other contaminants. We can imagine that over time, instead of having the plume expanding over miles, we have now contained it to within a single barrier. We've really concentrated that contaminant into a single localized area, which again makes it so we haven't expanded the problem, but also we have really isolated it to a much smaller area that could perhaps be addressed, by excavating it, or perhaps coupling it with any kind of developments in a destructive property or destructive technology that may be hopefully being developed as we speak. A second strategy is a pretty easy extrapolation from the first, which is now instead of using a single barrier, you use multiple barriers. This might be better for addressing a larger portion of a plume. So if you're talking about a large plume that you want to try and cut down, we can install multiple barriers. It's useful because instead of having to try and put in a grid to address the entire thing, you can let the natural flow of this plume help you out so that over time, again, the plume will be captured into these various points of the barriers. A third strategy I think is kind of an interesting one, and I think it's an optimistic one perhaps, but it's a great idea, I think, is that if you have an area where you're using some kind of a chemical and you know there's a potential, it's a potential source of a spill or perhaps a slow leak, you can actually preemptively control the formation of a plume by putting in this kind of barrier around it. And so you're going to fence in any kind of potential source and prevent a plume from even being formed. I think another way you could think about it is it could act as an emergency response. So you know that there is a spill, you can very quickly inject plume stop into the area to also keep it from expanding in that way. So again, here's the example where there's a spill, and instead of creating a plume, it has all been contained. And the fourth one really caters into the idea of the fact that these plumes really are very large, and perhaps it's just not feasible to address everything. So in this case, you could pick out various areas that really need to be cleaned up. So perhaps it's a well, again, perhaps it's some kind of body of water, and you can actually, kind of opposite of the last one, you could ring fence the sensitive receptor by basically putting in a Brita filter around it so that that particular zone is now protected. And as you pump through it, you're putting in a filter for the contaminated water to go through, so you can start to use this well again when perhaps it hasn't, perhaps it's been out of commission for a while because it's in the midst of this large plume. And just tying that back again, I think it's easy to see if we look at this map again, is that this entire plume may be really hard to address, but we could start taking out little pieces of it or protecting various sensitive areas by having the flexibility of plume stop to be able to inject into portions of it and perhaps, kind of trim down the plume, prevent it from growing, or reopen up wells or other areas that are currently out of use. So to review the benefits here of using plume stop to manage PFAS plumes, I think the first key is just the ability to inject this into the subsurface. We now have a new way of using activated carbon in situ because it is injectable. It has a good ability to flow, so it can be injected on wide centers, and it can also be injected at depth, which is going to help perhaps save some money. And as we went through in the modeling procedure, it really offers a tool to be able to have retardation factor as an engineering variable for the first time. And if we compare it to an ex situ use of activated carbon, we now have a passive plume control and containment strategy. So this potentially could be either coupled with or used to kind of deactivate a pump and treat system. So we can either avoid or decrease those O&M expenses that are currently associated with an ex situ pump and treat system. With that idea that it is it's a containment strategy, so we can prevent the growing of the problem. And the key part here is that it really does not interrupt any kind of groundwater flow. We don't see decreases in the conductivity with the injection of plume stop. And we'll end with sort of an optimistic idea here, as I've kind of pointed out a couple times, is that I do believe, a lot of people right now are working on destructive technologies, and I think it will hopefully be a matter of time before something is developed that can actually destroy, so we can talk about not just containing but also destroying. And in the same way that we have coupled enhanced biodegradation for other contaminants with plume stop, so we're able to sorb and then destroy, I think there's no reason why down the road with any kind of new developments we couldn't couple that new technology with plume stop. So right now we can perhaps buy some time, prevent these plumes from growing, but then perhaps down the road go back and couple it with the destructive technology. We'll keep our fingers crossed for that part of it. So with that, I'd just like to thank you all again for attending, and I've included my contact information as well as Chad's if you have any follow-up questions after today. But I think at this point, hopefully there are some questions that we can go through.
Yeah, all right. Thank you, Kristen. That concludes the formal section of our presentation. So at this point, we'd like to shift into the Q&A portion. If we do not get to your question, someone will make an effort to follow up with you after the webinar. So, okay, here we go. All right, so first question is, what about the shorter chain length compounds? Granular activated carbon is known to be largely ineffective for shorter chain lengths. Have you looked into this for plume stop?
Yeah, so that's a good question, and I think we do know the answer. As I mentioned, since it's based on activated carbon, it's going to have a similar type story. So yes, the shorter length chains will break through a little bit faster, just like they do in an ex situ system with activated carbon. They'll do the same with plume stop. And we are continuing to investigate a wider range of these to get all the isotherms. So yeah, I'll expect that they will break through a little bit faster. They'll be a little bit less favorable in their absorption. However, again, hopefully it's something we can design for. If we know the different components that are present in these plumes, we'd be able to make sure we put in enough plume stop to account for these. And we have the side of, less flux, lower flow rates going through us to kind of help us out to address that situation.
All right. Okay. Next question. You mentioned that at lower concentrations you get even better adsorption with plume stop. Is it possible to reach the low regulatory cleanup levels?
Yeah. So I described at the beginning that we have a tough problem in that we start off with low concentrations and we need to get to lower concentrations. And again, that's usually not the sweet spot for most technologies. That's usually where their efficiency drops off. The good news with activated carbon is it actually remains very efficient, and actually it's quite good at removing low concentrations. And so we have just confirmed that. We wanted to make sure that there was no issue there. So we've done a couple studies just to, I think we started with like a 40 part per billion PFOA or PFAS compound, and we were able to get concentrations well below that 70 part per trillion. So it is effective at these low concentrations, which is crucial in this situation.
All right. Okay, thank you. Next question is, how far does plume stop distribute once pumping is stopped?
Yeah, so that's a good question. So as we spent a lot of time looking at these columns, and we know that there is the plume stop does paint the subsurface, and that has a couple different mechanisms. The plume stop has an anionic charge to it, and most soil grains are actually anionically charged as well. And so we believe that there's one way that the plume stop adheres to the soil is through finding locations of positive charge, which allows it to electrostatically interact. Also, over time, the stabilizing polymer can begin to degrade, and that will also cause the plume stop to permanently kind of lose its stability and makes it stop in place. And that usually takes on the order of about 1 to 3 months. So you get the most kind of radius of influence upon the injection because there is a little bit of pressure applied. But then even after pumping stops, we'd expect to have some natural coating. Again, it's kind of like a brush stroke. You're finishing off that stroke and as you're painting it down, and that usually is about 1 to 3 months before you'd expect everything to be permanently locked in place.
Okay. Next question, how long will the water and soil remain stained?
Okay, so that's a good kind of follow-up there, is that it's going to look kind of similar. Actually, we can break that apart to the water and the soil. So the soil will remain permanently stained. Again, that's a permanent deposition. We don't expect that to go away. So, if you went and took soil borings, a couple, years, 10, 20 years, we'd expect to still see the plume stop there. So that is a permanent staining that occurs. As for the water, again, that's our mechanism. At first it's fully miscible with water, and it will continue to move through the water, but it ends up on the soil. So that goes back to the last question, that we expect it to be about 1 to 3 months that the water will remain black. And so, sometimes you see a little bit of black water, but within given the amount of time, 1 to 3 months. That also depends a little bit on what the soil type is, whether it's closer to 1 month or closer to 3 months. But that water will clear up eventually.
All right, we have a couple more questions here. So someone's asking typical cost.
Gotcha. So I might this is coming out of the R&D side, I might see if Chad has anything to add to that.
Sure, I'll give you a break there, Kristen. So if you can sort of envision a life cycle project cost timeline or a cost spectrum, with low cost on the end being more of a bio approach, and maybe on the high end, let's say thermal. We can probably all agree on those two extremes. If we're looking at the life cycle of the project, on the upper end of that spectrum is going to be essentially your mechanical systems. And then on the lower end of that half of the spectrum is going to be your more low-cost alternatives that are in situ approaches when talking about life cycle cost. And for plume stop, it falls more in that middle of the spectrum, kind of where you would be with application for maybe ISCO, in situ chemical oxidation type technologies. It's not an expensive technology to implement, relatively speaking, with our suite of different technologies that are available.
Okay, great. Thanks for your help on that one, Chad. All right, so next question here is, because efficacy is directly related to the ability of the material to disperse, does this preclude its use in fractured bedrock environments?
Gotcha, good question. I think the answer to that is kind of, the quick answer is no, it doesn't preclude its use there. It does require a little bit more investigation. So obviously bedrock comes in many different varieties. And you can expect that if it's really a crystalline kind of marble-like bedrock, there's not as much surface area for the plume stop to adhere to. So you're going to get it flowing through those channels for quite a ways. However, if it's a little bit more of like a weathered bedrock, there is going to be more surface area for it to adhere to. And in those cases, it might be a little bit more beneficial. We continue to work on optimizing different formulations to address scenarios like this. And so, we do believe that we have a solution for bedrock in that way too, to ensure that we do get enough deposition to get enough activated carbon in there to stick so that we can have an effective treatment. It goes a lot down to how well can we characterize it beforehand so that we can know as much as possible to make sure that we get the best possible placement at the end of the day.
All right. Okay. Thank you, Kristen. So we have another question here. Can there be re-injection after the plume stop is spent?
Yeah, that's a great question, and absolutely. We've done multiple reapplications and column studies, and there's really no reason why you can't go back and re-inject. In fact, that's a great use of, especially if there's injection wells. there's no downfall to putting more plume stop in a location where plume stop has already been. Again, we don't see clogging. It has the ability to transport it. It might put another thin layer on. You might actually see even more distribution to a wider area, but it is a way to get additional carbon. And I mean, that's a great, it might be a kind of a contingency plan, and also for more long-term treatment. We know that for something that doesn't biodegrade, it will break through eventually. And so if we need to put in more, it's absolutely possible.
Okay, all right. Thanks very much, Kristen. That will be the end of our chat questions. If we do not get to your question, someone will make an effort to follow up with you. If you have any questions, you see Kristen and Chad's contact information there. Also, if you need immediate assistance, please go ahead and visit regenesis.com, and you can find your regional technical representative there as well, and they will be happy to speak with you. Thanks again to Dr. Kristen Thorson and to Chad Northington, and thanks to everyone who could join us. Have a great day.